All right, good afternoon, everybody. I think we'll try to start approximately on time. So I'm Alex Snooren. I'm a professor at UC San Diego, although I've spent the past year as a visiting researcher at Google. So I'm delighted to session chair this upcoming session where we have 4 papers about really cool systems to help understand the performance of distributed applications. So the first talk is going to be by one of my colleagues at Google, actually, Junhua, who is a graduate of UNC. And actually started this work while she was a graduate student and continued it at Google. And so she's going to tell us about Fathom.
Thanks for the introduction, Alex. OK, so let's get started and talk about Fathom. Wait, let me share my screen.
So I don't. So I thought we just did funky P extend. All right, I'm on.
Oh, thank you. OK. Let's talk about Google's network instrumentation system called Fathom, which is designed for understanding the network performance of data center applications. So why do we need Fathom? Well, most Google services use RPC. We've long grappled with a fundamental challenge, the lack of comprehensive visibility into RPC performance in network stacks. And this deficiency has made it challenging to analyze and troubleshoot RPC performance issues. So to illustrate this limitation, let's consider Google's large-scale distributed tracing system, Dapr. So Dapr treats the network as a black box, and the time spent in the network is calculated from when the request is issued at the client until the response is received from the server. So unfortunately, this simplified view often attributes high RPC latencies to the network, disregarding the fact that there are many other critical layers within the network stacks, including the TCP, the rate limiter, the pacing, and link. And each of those layers is actually very critical for determining RPC's network performance. And this lack of visibility can cause significant delays in troubleshooting performance issues and also leads to an incomplete understanding of network infrastructure performance. So to address this issue, we've developed Fathom, a detailed network instrumentation system with wide coverage, low operational overhead, and high accuracy. So deployed for over 5 years, Fathom has become Google's primary tool for troubleshooting RPC network issues and evaluating the impact of network infrastructure changes. So what exactly does Fathom gather? As described earlier, the network stack has multiple layers, each with significant impact on RPC's network performance. So Fathom passively collects high-resolution kernel timestamps across in each of those layers for each sampled RPC, and calculate the latency spent at each layer by measuring the time difference. And additionally, alongside each kernel timestamp, Fathom also captures a snapshot of TCP connection statistics, including the congestion window size, the delivery rate, recurring timeout, etc. And those statistics can help identify performance issues. For example, they can help differentiate between RPCs limited by receiver's window size or those constrained by applications that simply don't have enough data to send. By collecting those 2 types of performance data, we get a very detailed view of what RPC experience in network stacks. So Fathom is meticulously designed to offer comprehensive coverage across our entire fleet while keeping the operational overhead low and maintaining high accuracy. So how did we achieve those goals? First, Fathom uses passive monitoring without introducing any interference or extra delays to production services. And secondly, Fathom focuses on RPC level tracing instead of more expensive packet level and applies sampling. And finally, to effectively manage the wealth of information without overwhelming our storage resources, Fathom uses the power of T-digest, which is a probabilistic approach that enables us to preserve distribution information of big data efficiently. So unlike traditional techniques like histograms, T-digest offers several advantages. For example, it facilitates the seamless merging of multiple distributions, eliminates the need for finely tuned bin sizes, achieves remarkable accuracy for quantile estimation, and does all those with minimum storage overhead. So with those techniques, Fathom is able to satisfy those key requirements. So next, let's dive into the high-level design of Fathom and its core components. So Fathom collects timestamps and TCP connection statistics as RPCs travel through different layers within the network stack. And to support different types of analysis, Fathom applies different sampling rate. So for real-time dashboard and alerts, Fathom samples every send message system core at 0.1% across all RPC connections in the fleet to ensure fleet-wide coverage with 10 different performance metrics. And for more detailed in-depth analysis of individual RPCs, Fathom uses existing depth tracing system that samples additional 30 more metrics every 128K RPCs, allowing users to thoroughly investigate the performance of a single RPC with our tracing UI. Furthermore, Fathom aggregates those detailed samples using T-digest. And this aggregated data is used for performing fleet-wide performance analysis and evaluating the impact of network infrastructure changes. So to give you more details, let's look at a practical example next. So in this example, we analyzed the performance of RPCs from a large-scale global infrastructure service with many different clients running on different server platforms. And this service was hosted in a data center with different NIC speeds. So within 3 days, Fathom samples over 1 million RPCs and aggregate them into around 50K T-digest. So when visualizing those T-digest in a three-dimensional space defined by receiver queuing latency, delivery rate, and round-trip time, we obtained 4 distinct blobs, and each occupying a unique locations within this space. Digging deeper, we analyzed the categorical attributes associated with RPCs within each of those blobs and uncovered 2 distinct attributes, the client type and NIC speed. For instance, in this plot, the green and orange blobs on the right belongs to the same client, client B, but RPCs in the green blob were running on top of fast-speed NICs, where RPCs in the orange blob were running on top of slow-speed NICs. Additionally, the persistent high receiver queuing latency experienced by client B suggested performance constraints on slow receivers, possibly due to exhausted CPU and memory resources there. And this discovery inspired us to model bottleneck constraints experienced by RPCs with multidimensional Gaussian mixture model. And it offers 2 primary advantages, as this example demonstrated. Firstly, it signified a substantial dimension reduction from 50K T-digest to only 4 distinct blobs. And secondly, even within those 4 blobs, we were able to effectively characterize RPCs based on their performance metrics and categorical attributes. And this level of interpretability enhances our capacity to gain insight from the data and offering a promising avenue for further analysis and improvement. So over the past 5 years, Fathom has been widely used in Google to evaluate and troubleshoot RPC performance. And all the Linux kernel instrumentation work is upstream to the mainline kernel. And our experience with Fathom has yielded several insights. Firstly, Fathom has been designed to address need and to scale. And it focuses on RPCs with lightweight and precise network instrumentation, which allows us to seamlessly accommodate the ever-growing traffic volume in our data center. And secondly, throughout those years, we have continuously improved Fathom's usability by introducing new components into the system. As a result, Fathom right now offers high-level annotation that pinpoint performance bottlenecks, as well as detailed visibility into individual RPCs. Furthermore, during our fleet-wide analysis, we realized the prevalence of Simpson's paradox in large performance data. While aggregate statistics can differ significantly from individual behaviors, potentially hiding subtle yet critical trends. And such disparities can lead to incomplete or even misleading conclusions for performance analysis. And for concrete examples, I'll encourage you to read our paper. And that's it. Thanks for your attention. And please feel free to reach out to us via email. Yeah. Thanks.
Okay, we have time for a few questions. I think there's a volunteer with a mic who's happy, a couple of them, if people have questions. All right, well, while folks are warming up, I have one, which is you've described a system that collects a tremendous amount of information for individual RPCs and then sort of aggregates it all together for fleet-wide. And I'm curious, which of those two capabilities have you found more useful or gets used more frequently in debugging problems?
So those two data are used in different scenarios. So for example, if a user experienced high latency for their individual RPCs, they can take a look at our UI, pull their detailed trace, and try to understand what is happening for individual RPCs that has problems. But we can't use individual RPCs for fleet-wide analysis, like the case study we showed there. So in that case, we have to use aggregate data, first because of the manual analysis is too much. If it's millions of RPCs. And also, secondly, like individual RPCs, they may differ significantly because each RPCs may experience may go through different paths or they go to different servers and we may show different performance variations there. So in order to get the whole picture, we need to look at them as a whole, like trying to understand the distribution from there to draw conclusive informations. I hope that answers your question.
Yes, question here. This is here, yeah. This is Mahmoud from Huawei. So in the 3D figure that you've shown, relation between RTT and Q-length and the rate, it was interesting that the correlation between Q latency and normalized RTT is not very correlated. So there's something going on that does cause the queuing that is not shown in the queuing and increase the latency, and some other things that does make even with the low queue we have high RTT, and even with high RTT we have low queue. So there's something to understand in this figure.
So RTT here measures the network round trip time, and the receiver queuing latency is the host delay on the receiver side. So we don't expect to see a direct correlation between those two.
So the queuing here is not for the network switches, it's the host side queuing, you mean?
Yes, so it's the time between when we receive the ACK of the last piece until the server start to process the request.
Yeah, this makes sense. Yeah. So, thanks.
Generally, future technologies. Great talk. I guess I might be biased because I'm also from industry. This it's established work. We also did something, methodology-wise similar, basically using like a system calls, grouped system calls, individual calls to understand the performance of single node. But going forward, right, I just wonder, in addition to the Simpsons paradox, any new challenges or new design target you guys are forwarding with? Not necessarily for specific, just trending, some trends, that's enough.
One direction that we think we can further explore is use more maybe ML techniques to make the most use of the data. Because we have enough data, but I don't think we're making justify for those data available. So I think like with some more advanced machine learning techniques, like deep learning to do this root causing across different RPCs, those, it can benefit us or not also. Yeah.
Okay, let's thank the speaker one last time. All right, and I'll invite our second speaker up. So Chao is a first-year PhD student at Peking University, where he's advised by Jin. He's interested in serverless cloud computing and like any good graduate student these days, ML. So he's going to give us a talk about Ditto.
Thank you, Alex. Now let me share my screen.
Advance to the next.
Oh, okay.
Oops. Where's the cursor? You see the cursor? There it is.
No, oh, here it is.
Okay. So, layer 2.
Yeah, hello everyone. This is Chao from Peking University. Today I'm very glad to share our work, Ditto, Efficient Serverless Analytics with Elastic Parallelism. This is joint work with Zili, Xinrui, Songyun, Gang, Xuanzhe, and Xin from Peking University. Recently, serverless computing is becoming an exciting cloud computing paradigm. Many cloud providers and open source communities are providing serverless platforms such as AWS Lambda and Azure Functions and so on. At the core of serverless computing is fine-grained resource elasticity and fine-grained billing. The resource elasticity enables users to easily scale up and down, and the billing policy ensures charges are only incurred for active running with 1 megabyte memory granularity and 1 millisecond time granularity. This makes serverless computing very cost-effective. These two benefits make serverless an attractive choice for distributed data analytics. As we can see, several works have ported data analytics applications to serverless platforms. Typically, these applications have a job execution DAG, which is composed of multiple stages, and each stage composed of multiple parallel tasks. Users deploy the tasks as a pool of serverless functions with two performance goals. First, we want the job to complete as fast as possible, which corresponds to job completion time, or JCT for short. Second, we also want it to cost as little as possible. On major serverless platforms, the cost of a function is the product of its execution time and the memory usage. And this paradigm introduces a new scheduling problem for serverless users. As we know, the number of parallel functions or the degree of parallelism, or DOP for short, affects both JCT and the cost of the application. And the fine-grained resource scaling of serverless enables us to adjust the DOP of each stage. For example, a stage with high resource demands can leverage higher parallelism for lower JCT, while a stage with low resource demands can use fewer parallel tasks to save cost. And here we are wondering, can existing parallel configuration solutions optimize the serverless performance goals? To answer this question, here we have a simple SQL query example with 3 stages. The widely adopted solution, which is applied by academic works like Nimble and is also Spark's default parallelism configuration. It adjusts the DOP of each stage following a perspective of data. So the DOP is proportional to the input data size. Intuitively, such adjustment is reasonable since the data I/O typically dominates in data analytics stages. However, for serverless computing, here we need to optimize this case to considering the data dependencies. Specifically, we need to increase the parallelism of stage 3 and decrease that of the other 2 stages to gain optimal JCT. In addition to considering data dependencies, the database method also suffers when the execution time is not proportional to the input data size. Now let's revisit serverless performance goals. We can observe that the most important factor for both JCT and cost is the execution time of each function. So in this work, we propose elastic parallelism to match the resource elasticity of serverless computing with parallelism scheduling in data analytics. The main idea is to optimize serverless performance goals directly from a perspective of time. However, achieving such elastic parallelism faces some challenges. First, elastic parallelism requires an accurate prediction of the execution time under dynamic parallelism. And as mentioned before, to calculate the optimal parallelism configuration, also need to consider the data dependencies, which can be very complex in arbitrary DAGs. Second, recent state-of-the-art serverless frameworks have proposed a shared memory for high-speed intra-server communication. This makes function placement relevant to parallelism configuration. Here's an example of a MapReduce job. The size of the circles indicate their execution times. We can choose high parallelism for the map stage, but the intermediate data should go through the slow remote storage, or we can decrease the parallelism to let the data exchange through fast shared memory. In the end, it is uncertain which case has a smaller JCT. And this slide provides an overview of how Ditto addresses these challenges. For challenge 1, we develop an execution time model to capture the time under dynamic parallelism and propose a DOP ratio computing algorithm to find the optimal parallelism configuration. For challenge 2, we greedily group stages with high shuffling overhead and combine it with the DOP ratio computing into a joint iterative optimization approach. Now I'm going to talk these designs in more detail. We observe that data analytics workloads are typically long-running and data I/O dominates in the execution time of these stages. So for these stages that perform data parallelism, the execution time is typically nearly inverse proportional to the degree of parallelism. Therefore, we modeled execution time as the sum of the parallelized time and the inherent time. The former represents a major overhead for processing partitioned big data and decreases as the DOP increases, while the latter stands for the constant overhead, such as function initialization. We can visualize the execution time by time units. Let's say alpha is 8 and beta is 1. When the DOP is 2, the execution time is 5. And when the DOP is 4, the execution time is 3. Now with the time model, we want to minimize the JCT for serverless analytics. Let's move to two basic conditions composed of two stages. First, for stages connected by data dependencies, the completion time of them is the sum of their execution times. In this case, we can formally prove that the optimal configuration for the two stages is that the ratio of their DOPs is equal to the square root of the ratio of their alphas. Second, for stages with the same downstream stage, the completion time of them is the maximum of their execution times. In this case, we can balance their execution times and get the optimal ratio of their DOPs as the ratio of their alphas. Besides, we can merge the two stages into a new virtual stage, which is equivalent in terms of execution time and also conforms to the time model. In this way, we can compute the optimal DOP ratios step by step for arbitrary DAGs. Please refer to our paper for detailed description. For the joint optimization problem, we use stage group to decouple function placement from parallelism configuration. Stages within a group should be placed on the same server to eliminate data shuffling overhead. Since the grouping problem is NP hard, we apply a greedy order that groups stages with high shuffling overhead first. However, for stages being grouped, their parallelized time parameters, alpha, will decrease since the I/O times reduces to 0, and therefore change the optimal parallelism configuration. As a result, we model the I/O and compute parts of alpha separately, and combine greedy grouping with DOP ratio computing into a joint iterative optimization method. Initially, we set each stage as a group and get the optimal parallelism first. Then we iterative group stages or stage groups with the highest shuffling overhead, and recalculate the optimal parallelism configuration in each iteration. We stop it when no more stages can be grouped. Now we finish the part of optimizing GCT. For cost optimization, we need to apply the serverless cost model in our algorithms. Please refer to our paper for more details. We build a system prototype of Ditto on top of Sprite. We implement the time model in the execution time predictor and the algorithms in the elastic parallelism scheduler. We evaluate Ditto on AWS across the 4 TPCDS queries that Nimble has evaluated. We use 1 terabyte scale data in the benchmark for evaluation. The results show that Ditto outperforms Nimble by up to 2.5 times on GCT across various settings, and up to 1 point time on cost. We also perform an ablation experiment to verify the effectiveness of distributed computing, greedy grouping, and their combination. For more evaluation results, please refer to our paper. Finally, I want to conclude the talk with 3 points. First, serverless analytics introduces the elastic parallelism scheduling problem to optimize serverless performance goals. Second, to address this problem, we propose Ditto to co-optimize parallelism configuration and function placement from the perspective of time. Third, Ditto outperforms existing database methods. This is the end of my talk. Thank you very much for listening.
Once again, have a few minutes for questions.
Generally, FutureWay, nice work. Just a ballpark back of an envelope calculation. You can have up to 2.5 performance improvement. If I remember your formula correctly, this sounds like Amadeus law, right? You have a sequential phase, you have a parallel phase, you can further improve. Does that mean the initial, the so-called, you call inherent phase, is like 40%? Yeah. What's the percentage of that time compared to the total original execution time? Is that like 40%? Just some random question, I guess. Yeah.
It depends on the stages, the stages in the queries. For typical big data analytics queries, the major stages that dominates in the queries execution time, the inherent time will, I think, will take about below 20%.
Below, okay.
Yeah.
All right, thank you.
All right, let's thank the speaker again. And then I will invite the third speaker to come up. All right, so for the third talk in the session, the speakers are getting younger and younger. Xinrui is actually a graduating undergraduate student. She's a fourth-year undergraduate at Junhua. Unfortunately for the professors in the room, she's already decided to continue for a PhD at Junhua. So, rats. But very much looking forward to her talk on DeepFlow, another system for distributed tracing.
Thanks for the introduction. So, hello everyone, I'm Xinrui, and today I'm presenting DeepFlow, and distributed tracing framework that provides non-intrusive data collection and rich network information. This is the joint work of Junhua University and Yunshan Networks. Recently, more and more applications are migrating onto the cloud, including e-commerce, online games, etc. Therefore, these systems are becoming more distributed, adopting various new concepts such as containers and microservices. But these technologies are double-edged swords. Indeed, they provide more flexibility and user-friendliness. However, they also pose some challenges. First, the invocation chain is longer and more complicated, making it more harder to find the broken point in it. Besides, the complex interaction between components that originally works well may also bring some new unexpected failures. Therefore, we need deep visibility into modern systems for faster problem resolution. Enters observability. Observability is borrowed from the control theory, and metrics, logging, and tracing are often perceived as the three pillars of it. Among them, logging focuses on natural semantics, metrics are the direct numerical properties, and tracing records the end-to-end journey of every user request, which is especially helpful under these new circumstances. Now, I'll use an example to see how tracing stands out from the 3 pillars and how current tracing tools have their limitations. So imagine you're a cloud operation engineer in an e-commerce company. BI developers one day report that their services are encountering end-to-end latency jittering severely. After a careful inspection of their app logic, they find nothing wrong, so they naturally blame to our network connectivity team and reach out to you for help. As usual, you open the monitoring panel of metrics, expecting several red-colored outliers to be the culprit. But this time, nothing happens wrong. All the metrics are normal. And indeed, although logins can contain more detailed information, without more clues and hints, it's kind of mission impossible to find the problematic parts out from tons of common cases, because this is jittering. This is not error, right? So without a tracing tool at hand, this problem stalls between these 2 developed teams, and customers are still constantly suffering from severe, unstable services. Now let's imagine what will happen if we have current tracing tools at hand, such as Jaeger. Now the BI team would happily show their evidence to cloud operators, which is us, that there's something wrong. Since both BI and Mongo components, they use the Jaeger APIs at their boundaries, so we can see clearly that at some traces, there's a long gap between BI sends a request and Mongo receives the request. Problem now successfully narrows down from the entire request to one hop, but unfortunately, it stalls again, because no matter how cloud operators test the communication between these 2 components, they still find nothing wrong. And now, let's step back and think again. What really happens between these 2 points? Is it really a network problem? We actually still don't know for sure. Because why? Remember that Jaeger is a manual tracing tool, which means only the spans directly defined in source code will be recorded, and all other unmodified components are still invisible. This is the time when DeepFlow can come for help. After deploying it on the fly, operators find something quite surprising. Actually, a hidden service occurs between Mongo and BI, and it is actually one of the instances of this component doesn't update to the newest version, which is account for the occasionally long end-to-end latency. So the issue comes from neither the BI group nor the cloud operators, but actually yet another third middleware group. Yeah, I know this might seem dramatic, but it's actually one of the real cases encountered in our DeepFlow clients. And I want to state that real world is never utopia. Non-intrusiveness matters a lot. Actually, because of the troublesome changes of passcode, operations team's efforts to improve observability aren't always supported by other developers. But with DeepFlow's non-intrusive, out-of-the-box tracing ability, no further effort will be required, and we kind of achieve this win-win situation. And I admit that there are also other non-intrusive or automatic tracing tools at hand, but they fail to meet other requirements, such as portability. A deep investigation of the requirements can be found in our paper. So now, without further ado, let's go to the system design part. How DeepFlow succeeds in meeting all these requirements? We actually have some insights from the eBPF technology. In short, eBPF provides a virtual machine in the kernel that enables the execution of BPF programs written by users at designated hook points, which is exactly what we need. And at the highest level, DeepFlow includes 2 parts, agent and server. An agent is deployed in each host machine to first capture trace data from the kernel space, and second, construct spans in the user space. The centralized server, on the other hand, stores all the spans collected from every single agent, and then combine them into traces. Besides, DeepFlow also provides rich third-party integration, including other spans under OpenTelemetry formats. To save our time, I won't go through implementation details. Instead, I would like to introduce our key design insights by answering the following 3 questions. First of all, where shall we capture trace data from? We proposed a narrow-waist instrumentation model with ingress and egress system calls. We observed that with a high degree of decoupling, the execution of microservice components are mainly triggered by its communication. Therefore, instrumenting all data communication system calls at component boundaries are well enough for basic tracing. What we provide is kind of a skeleton that is comprehensive for understanding the microservices, and those user-defined third-party instrumentations can fill in the flesh and blood of the skeleton. To some extent, I would say that this 10 system calls listed above is kind of the IP layer to the network stack as they is distant to the whole distributed systems. Secondly, how do we collect trace data using eBPF hooks? For the convenience of later assembling, we need to collect these 4 types of data: program, network, tracing, and syscall. Some of them are collected when syscall enters the kernel, and some collect the exit point. And the enter and exit information are combined with hash maps. Finally, how to assemble the collected data into traces. Traditional tracing tools often manually generate those per-request unique identifiers and propagate it along the message with specific headers, known as explicit context propagation. DeepFlow, on the contrary, changes nothing in the message. Instead, we claim that the network-related data collected by our eBPF hooks are well enough for the assembling algorithm into traces, and we call it implicit context propagation. As for the detailed hierarchical aggregation from data points to spans to traces, please again refer to our paper. Okay, we're now done with the system design, and let's move on to evaluation. Over the past years, DeepFlow has already identified over 71 critical performance anomalies for more than 26 company clients. Our paper presents 3 examples of them, and more of them can be found in Yunshan Network's website pages. We also conduct a testbed evaluation to demonstrate that DeepFlow's overhead is negligible for system being monitored. We first examine the trace collection overhead of DeepFlow agent and conclude that it only adds less than 600 nanoseconds of latency to each system call, which is acceptable for these long I/O communication APIs. We also conduct an end-to-end test over system throughput, comparing Jaeger and DeepFlow. The request per second is decreased by less than 7%, though somewhat larger than Jaeger's 4%. We collect 18 spans, whereas Jaeger only collects 4 under poor instrumentation. And note that DeepFlow can be used on the fly, so we don't need to constantly deploy it. In conclusion, evolving distributed scenarios such as microservices have new requirements on tracing frameworks. And DeepFlow meets all these requirements by first, establishing a network-centric tracing plane, and second, achieving implicit context propagation. We open source our project and have joined the cloud-native landscape as well as the eBPF project landscape. Please feel free to try DeepFlow out on our official website, and I'm ready for questions. Thank you.
Hi, Eddie Kohler, Harvard. Thank you. It's great. I was wondering, I could certainly imagine in some microservice deployments that there are other kinds of communication that happen. Can you talk about an example where DeepFlow was not able to connect an RPC together, and maybe what additional metrics you would want to collect with or without the help of the application so that you could knit a connection chain together?
So the question is, what are the things that DeepFlow can now do currently, right?
Or more positively, what would you want to collect additionally, or what are some future directions?
Okay, so currently there's a kind of thing that we have struggled with, that is message queues. Because as you see, the context propagation is implicit. We do not directly insert any kind of identifiers into it. although we use some network information that can help with the kind of one-on-one thread model, but with the message queues that have several threads in and several threads out, the information is not enough for us to infer the whole structure, and we are now working and thinking about new kind of possibilities with it.
Thank you.
Thanks for that question.
Hi, I'm Chung-an. I'm from the Toyota Motors. I have two questions. Great talk. Yeah. One question is to timestamp. Normally, we gather only the timestamp from the kernel, and monotonic only is how to gather the timestamp, the collaborated with the distributed tracing, the timestamp. The second question is the number of messages increases. We can consider the overhead from the gathering from the eBPF, such as the map or some other the gathering system. Could you introduce your overhead system?
Okay, thank you for questions. And as for the first question, I think eBPF already offers us the ability to collect timestamps at the kernels, and this is where we introduced in our second design point in the paper, and you can refer to it later. And as for the second question, I want to state again that in our test on this demo, the throughput influenced by DeepFlow is like less than 7% of overhead. And we accept that eBPF and these kernel hooks will have some influence on the system throughput, but DeepFlow is not always intended to use every time, all the time. It is on-the-fly deployment, which means we can switch on and off at any time we want without influencing the production usage. So it's just kind of for problem identification and resolution. We can turn it on when we have some problems and turn it off again when the problem is solved. So I'm not quite certain. I don't remember the correct number, but we do have a open source community, and you can have that issue on our GitHub page, and maybe some engineers will answer that later.
Okay, thank you.
Thank you.
Okay, thanks, speaker.
Thanks.
All right, and the final speaker in the session is Vipul Harsh. Vipul's graduating from the PhD program this year and is on the job market looking for a postdoc or industrial positions. And so he's going to be presenting his talk on Murphy, performance diagnosis of distributed applications.
Hello, everyone. My name is Vipul, and I'm going to talk about Murphy, which is a system for performance diagnosis of distributed cloud applications. Troubleshooting incidents in network systems is hard, and there are a number of factors which make this challenging. So there could be a large number of entities in the system, and these could be both virtual and physical entities, and might include VMs, flows, switches, hosts, service components, networking components, etc. And these entities might have complex dependencies between them. Another reason for complex troubleshooting is that the common monitoring data that's available is often coarse-grained. So typically, entities have metrics. So for example, VM will have a metric for CPU usage. And each of these metrics is a time series where each point is an aggregate over a few minutes. So this monitoring information comprising of entities and time series metrics is quite common in environments such as enterprise networks, cloud environments, WANs, etc. And so it's an important goal to automate troubleshooting using this telemetry. So in our work, we focus on this problem we call performance diagnosis. So let me define it using an incident that occurred in an enterprise network. So here, an application was not responding because its backend VMs were overwhelmed with high CPU usage. And operators wanted to reason about this problematic symptom of high CPU, but more generally, we can define a problematic symptom as a pair of entity and a metric of that entity which might have an anomalous value. So defining it this way allows us to capture other symptoms like high drop rate of a flow or high latency for a client. And the goal of performance diagnosis is to infer a root cause entity, another root cause entity in the system which is responsible for this problematic symptom. So in this incident, the root cause was a crawler machine which was sending a lot of requests to the front end to crawl the entire backend database. So in these works, a natural question that arises is what dependencies should we assume between the entities? And existing work falls on a spectrum here. So on one end of the spectrum are systems such as Explain-It, which assume no dependencies between entities at all. But if you assume no dependencies, you lose information about the topological structure that captures how these entities are organized in the system. And so this approach leads to poor accuracy. On the other end of the spectrum are a set of systems which are more restrictive. So for example, systems like Sage and Sherlock assume a perfect DAG of dependencies between entities. So in this DAG clearly defines how an entity affects another entity. There are no cycles in the DAG. So while this DAG makes the analysis easier, this DAG is also infeasible to get in many scenarios. And thus we are seeking a middle ground here, because in our enterprise network, we found out that there are a lot of cyclic dependencies. And there are two good reasons to model cyclic dependencies. One, there could be true cyclic influences between the entities in the system. So for example, VMs will affect the metrics of a host that they reside on, but the host in turn will also affect the metrics of those VMs. Furthermore, these VMs could talk to each other and influence each other's metrics via that connection. Another reason is that sometimes it might be hard to infer the direction of the dependency using the coarse-grained data that we have. So in those cases, we over-approximate the dependency by assuming influence in both directions. So because of these two reasons, we found out that essentially all application entities in our environment were involved in at least one cycle. So we really need to model cyclic dependencies. So we built this model, Murphy, for performance diagnosis, which takes as input a problematic symptom, which is specified by the operator, and it leverages common monitoring information and runs a 3-step analysis to produce its output. And the first step of the analysis is to construct a model of the entities and the dependencies between the entities. So the idea here is that instead of using a causal DAG, we'll use this idea of using a general relationship graph. So here in this graph, the nodes of this graph are the entities in the system, and the edges are based on these loosely defined neighborhood relationships rather than basing them on causality. So for example, here we add an edge between a VM and its host. We add an edge between flows and the endpoints of that flow, and similarly for other entity types. So using this general relationship graph allows us to capture the topological structure that's naturally present while still allowing for allowing us to capture complex and cyclic dependencies. Okay. So the second part of Murphy is to find the root causes in the model. So just to recap, our goal here is to find another root cause entity in this relationship graph which might have resulted in the problematic symptom. Now, if this were a DAG, then we would know exactly which other entities affect this problematic symptom and how. But since it's not a DAG, we need another inference algorithm, a powerful one, which can find root causes in this general relationship graph. So the first step of inference is to learn a joint probability distribution on all entity metrics. But how do we learn such a distribution? Note that the relationship graph is not a DAG. It might have cycles. We don't know the direction of the dependencies. So this is where a Markov random field comes into picture. So a Markov random field, or MRF, is a way to define a distribution on top of a general graph. And we learned this MRF via historical data from some time before the incident. So at a high level, this MRF captures local properties of an entity. So for example, if we say that it captures things like, if the neighbors of B look like something, then what should be the likely value of B? And if the neighbors of C look like that, then what should the value of C look like? And so on. So once we have this distribution, we can use it to answer counterfactual queries, such as, if we change the value of A, would it make the high value of D go away? So how this works is, first we pick a different value of A, let's say A star, and this might be a lower value. So assuming the newer value of A, we resample B, and similarly we resample other entities, assuming the newer values that we resampled before. And we run this resampling process a few times so that any cyclic effects in the relationship graph get propagated. So at the end of this sampling process, we end up with a new value of D, which is a consequence of starting out with a different value of A in the first place. And if this new value of D is significantly less than its original value, then we conclude that A is a root cause for D. So this gives us a way to say whether A is a root cause or not, and to produce the list of all possible entities, all possible root cause entities, we simply iterate over all entities in the candidate pool and check them one by one using this analysis. So in this relationship graph, using this algorithm, Murphy identifies that these three entities are the root causes for the problematic symptom. Now, the analysis ends here, but we also found out that it was useful to attach simple explanations to the root causes. So to do that, we trace the likely chain of influence from the root cause to the problematic symptom, and this allows the operator to better interpret the root causes that Murphy produces. So here is a scenario in a microservice app where a client is experiencing high response times. So client 1 is experiencing high response times. And the reason is client 2, who's sending a lot of requests to another API in the application, API 2. Now, there is performance interference between these two clients who are accessing different APIs, because there might be a common service which is shared between API 1 and API 2. So now if we wanted to model the effect of the clients on the backend service and then back from the backend service to the client, we would need to handle these cyclic effects. So in this scenario, Murphy found the root cause with high accuracy, whereas other systems did not perform as well. So here is another scenario where the problematic symptom is high response times for a client, and the root cause is a container which has resource contention. So this scenario is inspired by past work, and it does not require us to capture cyclic dependencies. So Murphy should also do well here. And it does. In fact, both Murphy and Sage do well. Sage is a past work for this in the absence of cyclic dependencies. Murphy is marginally better than Sage, probably because in our environment, we didn't have enough data points to train Sage's neural networks. And finally, we tried our schemes for some production incidents in an enterprise environment, and we found out that Murphy produces 5x fewer false positives while achieving the same level of false negatives. So that's it. Please check out our paper for more details, experiments, and design. And we also have a blog post from VMware, which talks about commercial adoption of this project. So please check that out, too. Thank you.
Hi, Shir from the Open University in Israel. Very cool work. Just a question, do you guys, is Murphy able to cope with like short-lived events like microbursts, or does it take that into account at all?
So it depends on the length. I think if it's like if it gets captured, so the information that we assume is already coarse-grained. It's over a few minutes. So if it happens within the interval, then it's just not in the monitoring information for us to capture it. But if it's over a few minutes, then yeah, we can deal with that.
Okay, thank you.
Thank you.
Khaled Diab, HP Labs. Nice work. So in the MRF, does the relationship attenuate as the length between the dependencies increase? Because you are multiplying all the probabilities with each other.
Mm-hmm.
Thanks.
In general, that does happen because naturally the influence will get weaker. So it does happen, but if there is an influence that's so we have tested cases where the chain of influence is long, but Murphy was able to capture those as well. But in general, yes, it does happen. It's a phenomenon.
Hi, I'm Abhilash. I'm a student at Columbia University. So I had a question about the directed acyclic graphs that you were talking about.
Mm-hmm.
So I was wondering what was the amortized time complexity that you kind of estimated for this problem? Because in order to estimate that there's a problem in node in a specific source vertex, in order to determine that there's a problem in a specific vertex,
mm-hmm.
you need to go through all of the nodes in the graph. And for each of the nodes that you change a value, you need to also look at all of how that value propagates across the graph to
mm-hmm.
eventually identify that there was a problem with that specific source. And you need to do this for all source vertices in the graph.
Right.
So I was wondering what is the complexity you're looking at in terms of algorithms?
Right. So we do, so if there are a really large number of components, we do cut off by distance from the problematic symptom. So we'll filter out everything that's outside a radius of, let's say, 4 or 5 hops. But in general, it's something like order n, because to evaluate each entity, it's really not that much. We resample a subset of entities. And just to give an idea of the runtime, in an enterprise environment, we were able to run, Murphy took about a minute to a couple of minutes to run for one symptom.
But you did say you do some sort of optimizations, like cancel out some sides of the graph based on how you see the graph is propagating?
Yeah, we do. We do some sort of filtering, yeah.
Right.
In case the graph is too large, we do that.
Right.
Yes.
Fantastic. Thank you.
All right, well, let's thank the speaker again. And then
Thank you.
I'd like to invite all the speakers up to the stage. We have time for a quick panel session. So this is opportunity for the speakers to ask questions of each other. If any of you have a question, go ahead. Otherwise, I have one. Oh, go ahead.
So I had a question about DeepFlow. How do you handle the different threading models that exist? Because applications might have all sorts of threading models where a request comes in, it gets processed by a different thread, and then gets passed on to another thread. So how do you map the incoming request to the outgoing request when you have asynchronous patterns or batching or other kinds of threading patterns?
Okay, good question. Thank you for that. I think this refers to how we correlate the data we collect into traces and spans. Mm-hmm. And we use kind of various network communication protocols. The insight is the request and response might use the same protocol. For example, HTTP3 or RPC or some customized protocols. And we kind of iterate through these protocols to first group them into different network protocols, and then use some protocol-specific headers and that sort of thing inside it to do that correlation.
I see.
Yep. Okay. And for this user-defined ones, we have an API to define what the users use of their own. So
Thank you.
So we saw some graphs about CPU overhead and performance overhead of the tracing. I don't think any of you talked in the talk about the storage requirements. And if these things are running in production, I could imagine a tremendous amount of data. So I'd just be curious if you each had any comments on the complexity of managing that in your system.
Good question, and our team is actually working on that. We are thinking about how we can kind of aggregate traces into some aggregating form to reduce that storage overhead, and hopefully we can post it on other conferences.
Yeah, so in our case, we have different retentions for different types of data. So for the individual RPC tracing information, we only keep it for a few days because the data size is huge. For the aggregate data, we can keep it for like up to 1-2 years. So yeah, that's our budget.
Okay, I want to ask a question about Fathom. I want to, as I'm not an expertise for network measuring, so I'm wondering how can Fathom be complementary to the application's whole life cycle and to give users a more accurate performance diagnosis. In my opinion, now Fathom just measure the network round trip and the RPC part of the applications. Yeah.
So so right now we have a set of heuristic rules that we check all the latencies we measured in different layers, and based on those latency, we have a decision tree-based heuristic rules that give user estimation about what might be the bottleneck. It's not like 100% perfect estimation, but it works. But that's the reason why I'm saying maybe in the future we can use some more advanced ML techniques to further improve that. Yeah.
Okay, thank you.
Thanks. So those are great questions. I want to thank again the speakers. All did a wonderful job.
Thank you.
So I'd like to encourage those of you with more questions, please come up. I'm sure they'd be happy to answer your questions one-on-one. We have a very brief break, 15 minutes for the next session, and will the speakers for the next session please meet the session chair? He's waving his hand here in the corner. Thank you all. Nice job, everybody. Thank you. Don't forget your